Okay, so now we're going to work on solutions 2. Just give you a heads up, I have deleted a couple slides that I've determined you guys really don't need to know for the regents, so I don't want to add anything extra for you guys to have to look at. So we're going to look into concentration some more. Remember, concentration is parts per million, molarity, and then based off that, we're going to look a little bit into colligative properties. So again, remember molarity, it's moles of solute into liters of solution, which then you have something called molality. That's moles of solute in kilograms of solvent instead of liters. All right, so a real quick exercise in the yellow pages. What is the molality of a solution by dissolving 2.5 moles in a solute of 525 grams of water? Now, again, when you're looking at this specific formula, this is specific equation, you're looking at kilograms, not grams. So this is in grams. What you have to do is take the decimal from here, 1, 2, 3, and then you're going to get 0.525 kilograms of solvent. That's how I get this. Put it over 2.5 mole, or under 2.5 moles of solute over solvent. Calculate it out, you get 4.76 little m, but definitely be careful with the little m. I think this is more of a cursive little m than like a meter m, which is a print m. Okay. All right, so what is the molality of a solution by dissolving 125 grams of glucose in 0.5 kilograms of water? Yay, kilograms is great, but then they gave us a little twist by putting 1.25 grams instead of moles. So what do you have to do? Anytime you're given grams, you have to go to moles, use your gram formula mass. So we're looking at glucose. Glucose is C6H12O6. If you do the, 6 times 12 plus 12 times 1 plus 6 times 16, you'll get 180. I was asked, well, where this 1.8 come from? That's if you were to add a couple extra after the decimal place. Okay. All right. So if I was to do this, I'd do 125 grams times 1 mole over 180.18. Now, that's because I got to get rid of the grams. Say I wanted to go from moles to grams, you do the reverse. When I calculate it out, I get 0.694 moles. All right. Oh, pardon me. So I'm going to take the moles, moles of solute over kilograms of solvent. I plug this in. When I calculate it out, I get 1.38 molality. All right, what is the molality of the solution made by dissolving 39.5 grams of naphthalene in 428 grams of toluene? So these are the molecular formulas for both the naphthalene and the toluene. Remember, molality is moles of solute over kilograms of solvent. Again, I'm going to have to go from 39.5 grams to moles. So it's 10 times 12 plus 8, so 128. Again, the 8.18 is for the extra after the decimal place. When I calculate it out, I get 0.308 moles. Again, over kilograms of solute. They put it in grams. So not only did you have to use the gram formula mass, but you have to convert to kilograms. So 1, 2, 3. 0.308 over 0.428. When you calculate that out, gives you 0.720 molality. All right, so I just skipped a couple things. I think possibly, or I'm going to be skipping some soon. So colligative properties. We've already seen this, but now we're putting a name to it. So solutes, like the Kool-Aid putting into the water. That's the solute. So solutes create an interface to certain phase changes of a solvent, like water. Water is the solvent, the bigger amount with a small amount of solid put into it. So properties of solutions differ from those of pure solvent. So like pure water is different from a solution of like salt water. To change, the change in colligative properties depends on the number, not the type of solute particles present. So I'm not necessarily looking covalent versus ionic. I'm looking how many particles are actually combined in the solvent, in the solution in the solvent. So what do these properties involve? Freezing point, boiling point, vapor pressure, osmotic pressure. We're not really going to look too much at osmotic pressure, so don't worry too much about that. So, pardon me, real quick, these are in double pages, so bear that in mind. Adding solute to water will lower its freezing point and raise its boiling point. I remember we talked about this when we were talking about adding salt. Remember, you add salt to it, you are raising the boiling point. You're not making it boil faster. So in essence, you're cooking at a higher temperature, which cooks it faster. It doesn't boil faster, it cooks it faster. Whereas where you put salt, rock salt, let's be specific, rock salt onto ice, and that melts the ice, making the ice's freezing point lower, which actually does melt the ice. So the overall effect is that water solution stays in the liquid state over a larger range. Using molality, the new freezing and boiling temperatures of any solution can be calculated using this formula. Now, you don't need to know this formula. We're not going to do any of the exercise on it. You don't need to know it. Just know, yes, because of molality, we can then determine the new freezing and boiling points, okay? So the nature of the solute, this is on 2 different pages. By the way, 2 different sets of notes for you guys. So the nature of the solute, the stuff you put into the solvent. So say I have a 1 molar solution of glucose, sugar, and a 1 molal solution of sodium chloride. Pardon me. A 1 mole solution of a glucose and a 1 molal solution of sodium chloride do not freeze. These solutions don't freeze at the same temperature despite having equal concentrations. I believe this is molal, this is molal. They're the same molal, but they don't have the same freezing or boiling point. The difference is due to the fact that one is molecular, covalent, like glucose, and one is ionic, sodium chloride, metal-nonmetal. Ionic compounds are termed electrolytic. You might have heard of electrolytes before. That is an electrolytic solution that you're drinking, because the ionic compounds are dissociated in water. Remember the ionic equations, to produce ions, which will then conduct electricity. So you've got NaCl, aqueous solution, which breaks up into sodiums and chloride ions. So for 1 mole of glucose, 1 mole of interface is created. When I drop this in, it's not going to break apart into the different ions because it's covalent. They're sharing. They're not taking. So you literally have all these molecules in there. Whereas when I throw in sodium into water, it breaks up into the ionic compounds of a sodium ion and a chlorine ion, which means I have 2 moles in this as opposed to 1. So write the dissolution for each of the following. How many moles of particles will be produced for each? So looking at this, CaCl2 we know is ionic because calcium is metal, chlorine is a nonmetal. So they break apart into the ionic equation with calcium 2 plus 2 chlorines. Remember, when you have this, you're not messing with this part here. You're actually adding it. There are 2 chlorines. So altogether, I add these up and you actually have 3 moles. Let's look at aluminum nitrate. There's 1 aluminum plus 3 with 3 nitrates. Now you may say, hey, but Miss Co, there's 3 oxygens here. The reason why I'm not messing with it is because it's a polyatomic ion. You do not mess with the subscripts with polyatomic ions, which means when I add up all of the moles here, I've got 1 here, 3 here, 4 moles altogether. C12H22O11. Well, this is nonmetal, covalent, which means it doesn't break up, meaning there's only 1 mole. All right, so let's look into osmosis. This is the net movement of solvent from pure or low solution region to a high concentration. So they're going to go from high to, or from low to high, low to high. So at first we have a high pressure here, low pressure here. At equilibrium, everything will equal out. Less of these will be there, right? Like less water molecules, they'll go across, right? Look, there's more going across here than going across here. Now there's equal, where there's more here giving you osmotic pressure. Again, we're not really going to look too much into it. Just know that the pressure needs to stop. Such movement is called osmotic pressure. Pressure needed to stop the movement going across a membrane. All right? As a solution is added to a solvent, its osmotic pressure increases. Intravenous fluids, this is just some stuff that you should know. Intravenous fluids must be isotonic, same as osmotic pressure, with body fluids. For instance, red blood cells in hypnotic, less than concentration fluids, water moves into the cell, causing a rupture, hemolysis. In hypertonic, more concentrated fluids, water moves out of the cell, causing a collapse, crenation. You don't want like any of this to happen, which is why you're given intravenous fluids. So dialysis, this also brings up dialysis. So dialysis machines use artificial kidneys to purify the blood. The cell membrane allows the transfer of both solvent and solute particles. So looking, waste products dialyzed out into the washing solution. So the impure blood comes out, gets rid of the waste, it purifies the blood, goes back in. Dialysis results in movement of waste particles into the washing solution, cleaning the blood. This is where that osmotic goes. That low concentration goes into the high, high goes to low. So in this, impure has high, which is going to the low water solution. It cleans it out. Okay, so just looking at the colligative properties, try solution terms, match them up, do the crossword. If you have any questions, please don't hesitate to ask. Hope you guys have a great day.